Welcome to this explainer. Today, we're diving into an absolute paradigm shift in artificial intelligence. For the past few years, the entire tech world has been totally captivated by systems that just predict language. But right now, we're crossing the next frontier. We're moving from predicting words to predicting physical reality itself. It's a fundamental leap from generative language models to something known as world models.
Okay, let's kick this off with a really simple thought experiment. Picture this, you're standing on a sidewalk and a car drives past you, disappearing behind a massive tree. Now, as a human, you've naturally got this thing called object permanence. Your brain absolutely does not think the car just ceased to exist just because it's out of sight. Instead, your brain has built an internal simulation of the world. It intuitively knows the car is still there, moving forward, and is going to pop out on the other side. You don't consciously do the math, your brain just gets it.
And it's exactly the same when you're riding a bicycle or, say, catching a baseball. Our internal mental models are constantly processing these vast amounts of sensory data to reflexively predict what's coming next. Navigating a crowded sidewalk, your brain is running a subconscious, real-time simulation of physical reality. You're constantly predicting the future based on the laws of physics, gravity, and momentum, long before your muscles actually make a move.
So here's the real kicker. A world model in AI is fundamentally entirely different from those large language models we're so used to chatting with. Instead of just guessing the next word in a sentence, a world model is actually attempting to simulate the complex dynamics, the physics, and the causal relationships of a physical environment. It's constantly asking, if I take this specific action in this space, how will the physical reality around me actually change?
All right, Section 1, a history of predicting reality.
Now, you might think world models are just this sudden new trend, right, driven by some recent flashy tech announcements. But actually, they are part of a decades-long scientific quest to give machines a genuine grasp of our physical environment. We can literally trace this all the way back to the 1940s with Norbert Wiener's theories on cybernetics. Then in 1990, Jürgen Schmidhuber officially drops the term world model into machine learning. Fast forward to 2018, and David Ha, along with Schmidhuber, published this landmark paper where AI agents actually learn to drive inside their own hallucinated dreams. And that entire journey has violently accelerated into the highly advanced architectures we're seeing today. Things like Yann LeCun's JEPA and the massive recent releases of NVIDIA's Cosmos 3 and DeepMind's Genie 3.
And through all those decades of research, the core underlying goal has been rock solid. For a system to be truly intelligent, it relies on a very specific feedback loop. It has to perceive its surroundings. It has to internally simulate potential futures based on what it sees. And then, crucially, it has to adapt its actions based on that simulation.
Which brings us to Section 2, from words to worlds.
When we make this leap from language to reality, the complexity absolutely explodes. LLMs are basically operating on a one-dimensional, sequential signal. They're generative, just predicting token after token. But world models, they are trying to model physical reality itself. I mean, here on Earth, that means dealing with incredibly chaotic variables, strict geometry, and super rigid physical laws like gravity and momentum. You can't just guess the next pixel the way you'd guess the next word. You actually have to understand the fundamental structure of the space.
In fact, AI pioneer Dr. Fei-Fei Li points out that the scope of this challenge goes way beyond anything AI has ever faced before. She calls this new frontier spatial intelligence. The core idea is that true intelligence demands an explicit representation of physical reality and spatial relationships. Basically, that intuitive understanding of the world that we humans develop naturally right from childhood.
Moving on to Section 3, the great AI architecture debate.
So everyone agrees we need world models, but there is a massive, ongoing scientific debate about exactly how we should build them. It essentially splits into two camps. On one side, you have the generative approach. They believe if we just scale up generative models enough, they'll naturally develop world understanding by literally predicting every single pixel of a future frame. But the other side, heavily championed by Meta's Yann LeCun, argues for a predictive approach. They say true intelligence strips away the noise to focus purely on structural meaning, predicting outcomes in what's called a latent space, which is basically a highly efficient, simplified mathematical representation of the world.
See, the generative approach runs into a huge wall. Think about trying to predict exactly how the leaves on a tree are going to rustle in the wind. Forcing an AI to predict every chaotic little detail wastes ridiculous amounts of compute. And worse, when it faces uncertainty, it usually just spits out this blurry, averaged-out mess of possible futures. A predictive latent world model, on the other hand, completely filters out that visual noise so we can focus on understanding the actual structural path of what is happening.
LeCun's Joint Embedding Predictive Architecture, or JEPA, is a perfect example of this.
In this framework, the AI isn't trying to draw a literal, pixel-perfect picture of the future. Instead, a perception module takes in sensory input and projects it into that mathematical latent space. The world model then predicts what will happen next within that abstract space. Finally, an actor module uses that understanding to plan optimal actions. It's predicting meaning, not pixels.
Let's dive into Section 4, Robots, Sims, and Synthetic Data.
Now you might be wondering, why are the biggest tech companies on the planet throwing billions of dollars at this? Well, it's about incredibly practical, real-world utility. World models are a total game changer for embodied AI, like humanoid robots or self-driving cars. Think about it. You definitely can't safely test a self-driving car in a freak tornado on a public highway. But inside a highly realistic, risk-free virtual world model, you absolutely can. This lets companies bootstrap robotics training, test crazy edge cases, and generate mountains of physics-based synthetic data safely before any hardware ever touches the real world.
Just look at what Google DeepMind is doing with Genie 3. This isn't just generating a short static video clip, it is a full-blown simulation platform. It procedurally generates photorealistic, persistent 3D worlds from simple text prompts, and it does it in real time at 24 frames per second. Most importantly, it actually maintains object permanence. Companies like Waymo are already leveraging this tech to build specialized simulations, stress testing their software against rare scenarios they almost never see on actual roads.
And we're seeing massive parallel moves from NVIDIA with their Cosmos 3 models. To give you a sense of scale, they train this on 9,000 trillion tokens. That equates to roughly 20 million hours of driving and robotics video. They're releasing these open-weight baseline models to give developers powerful tools for spatial reasoning. It's essentially democratizing physical AI, making it possible for developers everywhere to build next-generation robots and simulate insane virtual environments.
Finally, Section 5, the unresolved path to AGI.
Okay, despite all these incredible breakthroughs, we really need to take a step back and maintain a calm, analytical view of where we're actually at. World models are absolutely not some guaranteed magical golden ticket to artificial general intelligence. There are still massive hurdles. Right now, almost all the success is heavily concentrated in computer vision, and there is zero proof yet that this will perfectly translate to broader cognitive reasoning. The computational costs are still astronomical, and there's fierce academic debate. Some critics are literally asking if predicting in a latent space is really just autoregression in a fancy disguise. We honestly just don't know yet if scaling these physical models will actually lead to true general intelligence.
But as we watch this tech evolve, it really challenges everything we thought we knew about AI. It leaves us to ponder this incredibly profound scientific question. Does true machine cognition emerge simply from predicting vast, endless amounts of sequential data? Or does intelligence fundamentally require building a persistent internal model of reality itself? It's a massive question, and researchers are going to be wrestling with it for years. Thank you so much for joining me on this explainer, and definitely keep your eyes on the physical world.